So we are going to continue with this second block about 3D. The next presentation will be server-side data fusion in 3D mapping with VTS by Ladislav Horký. So whenever you want.
Hello, I'm Ladislav from Melon Technologies. You may remember me from yesterday's presentation. This will be kind of, it will continue a bit more in the presentation, but on server side, you may remember it was about how to get started with 3D application development, and it was mostly JavaScript. So let's dive into server-side fusion in 3D mapping with VTS. First, I'm not sure how many people came. I'll just go very quickly through the company intro. So we, Melon Technologies, are a software development company in 3D mapping business. We have two projects. First is in-house photogrammetry engine. Together with deep learning, we basically process aerial imagery into photogrammetric meshes, photogrammetric 3D models, and then extract our semantics from the models. The second, our big project is fully open source. It's VTS 3D geospatial stack, which uses the outputs, our 3D models, and also 3D models from third-party software together with DEMs, DSMs, orthophotos, vector data, fuses them together. That's what are we going to talk about today, and streams them to various clients across desktop, mobile, web, Unity, or, for example, ArcGIS. Applications are virtual reality, augmented reality, interactive simulations, gaming. We have the Unity plugin, and geospatial 3D mapping. So what are we going to talk about in this talk? So first, let's look at some motivations for data fusion. Then we will look on how to actually do the data fusion in VTS. And we will also, I'll show you some live demo for that. So, data fusion, motivations and approaches. The data fusion is kind of a buzzword, like everyone does it somehow, or at least everyone says they do it. So what is it actually and why we do it? So the data fusion is basically about displaying together heterogeneous data. Like we do it for a number of reasons that I'll describe later, but the data can be various in type, in time, and in resolution. In type, for example, you can have terrain models, you can have orthophotos, which are like totally different data sets in nature. You can have 3D, you can have vector data, you can have some multispectral data, and so on. In timestamp, that's clear. You have the same location captured in different times. Resolution, again, different resolution. Here are the examples. Here you have 3D together with vector data. So that's like fusion of different types of data. We can have the same location captured in different times. So here you can see some changes, for example. And of course, we have different resolution. So why we fuse it like all together or try to display it all together? So it's mainly because we want to find the connections in the data. It's usually like when you get some new data, the first thing you do with them, you try to display them with something you know, to maybe try to eyeball something before applying some standard analytical processes and so on. So it's really important to actually see the data together, and it's also important for verification of your results. If you find, okay, so here is something interesting, but I don't see it in the data when I look at it. It may ring some like warning bells and so on. Then we want to watch for the changes in time. For example, we saw there was a new building in the model, so that's another option. And for resolution, we want to see both the details and the big picture. And we are talking about 3D data fusion, so why 3D is important for this? Well, the 3D can make all of these changes, connections, and relations much more obvious. For example, if we go back to this building, If you have just 2D data, you know there's a new building. But if you have different time snapshots and you want to know how many floors have been built since the last snapshot, it's very hard to tell with 2D. And 3D is really good for that. For example, if you have some like weather radar, you may notice, if you have the mountains in 3D, you may notice better what, like the local weather, how they can influence local weather than from just 2D map. It takes more trained eye to do it from 2D map. From 3D, it's really more obvious. So 3D makes the changes more obvious. What are most common approaches to the data fusion? A bit paradoxically, I would say the most common approach is to do no fusion, just basically take all the data you want to display and just display them together. That's great because you can work with the data on the client wherever you display them, because they came independently and you just can turn them off, on, and so on. So that's great for the work with the data. But of course, it has some downsides. For example, it's very resource intensive usually. You may, if you do it like really no fusion, like without any optimization, you end up usually rendering same thing many times. You'll end up downloading the similar data many times and so on. And the result may be not always so nice because the client has usually some limitations how it can render various things. Usually it will do the fusion using the Z buffer and so on, but it has its limitations. So that's one approach which is really good for work with the data. The second approach is kind of like fuse them all approach. That means that you fuse all the data you have already on the server into one opaque structure and stream it to client. This great example for this is current Google Maps 3D base map. You just go to Google Maps and you see whatever Google serves you. Like no one expects you will want to see another orthophoto. You will want to switch orthophoto. You will want to like turn on more detailed terrains or turn off the cities. No, it's just one opaque structure, and above it you have some basically a very light GIS application. So yeah, that's it. It's great for WebGIS because in WebGIS or the user-facing applications, you don't really have control over the client's resources. You don't know if you can if the client will handle the rendering of some complex things. So you want to keep things very simple for the client, and that's ideal for it. This has probably the lowest possible load on the client because you just send one thing to the client and say render it, and it will. But of course, again, downsides, it usually results in static data. So you have one big chunk of data lying somewhere on the server, which may be kind of hard to update or to work with. And of course, on the client, you can no longer retrieve particular resources. So when we started to produce 3D models, we had to tackle the same problem. We knew that we will have more 3D models than just one. We wanted to add some context, and mainly we focused on very fast and lightweight clients. So we naturally started with a fuse them all approach. It was good until the data grew a bit, and then it became a really like tedious job to actually maintain the data set, the whole fused data set. The update operations were extremely fragile. You had to basically back up all the thing before any update. And we also aimed to include some global terrain, for example, like global DEM. And this approach would result in unbearable large data. So it was impossible to do it with this approach. And also we were impossible to do the things like you don't do on the Google, like switch textures, switch terrains, and so on. So we came up with something like action plan for VTS when we summarized what we want VTS to handle, what we want VTS to do really good. And one of the things is including the dynamically generated global data sets, because you don't really have space to pre-generate the whole like terrain in 3D. So we want this to be done dynamically. We want to improve the manageability of the data on the server and at the same time, allow the client to work independently with the datasets and maintain good client performance, which basically means we wanted to combine the advantages of both approaches, the no fusion approach and the fuse them all approach. So since that, we have developed VTS with all this in mind. So VTS is now, it's an integrated platform. It contains both the servers and the clients. It got eventually open source under BSD2 license. It's scalable and high performance because it was also used in the project my colleague described in the previous talk, and still has lightweight clients. I'll just go briefly what servers it features. It has the data fusion capabilities we needed. So just briefly about the structure. It has two servers. The map proxy, the one that takes care of the dynamic, not only terrain, but generally dynamic tile generation for terrain textures and vectors. And VTS daemon, which serves static content. And then we have many client APIs for web, for desktop in C++ and Unity in C#. So let's see how we can actually do some data fusion in VTS. So let's start from some like very basic thing. Let's just combine terrain and orthophotos. So how we do it. So in VTS we call terrain a surface because it's something we can project something on. Orthophotos are, and textures we count bound layers because they can be bound to the surface. And they are both streamed dynamically from map proxy based just on some slightly preprocessed GDAL rasters, WMS or WMTS. To fuse the terrain in future, to fuse it, for example, with the cities or with more detailed terrain and so on, we add the terrain actually to VTS storage where the fusion is performed. For now, basically it's no op because there is like nothing else in the storage. And we create a map configuration which tells basically the client what we want to display or what resources we want the client to see, and the client can then pick and display what it needs. So we create a map configuration file that describes how those textures will be bound to the terrain. So we have like one terrain that's like 180 meters viewfinder. It derived from Viewfinder Panoramas DEM, if you know it. It's some really nice global DEM dataset at 90 meters. Yeah. We have two bound layers, one global, it's blue marble, and one small square local VHR imagery. So this is how we combine it together. We basically tell where the storage is, say we want this tile set from the storage, defined where the definition of bound layers lie on the map proxy, and tell the client we want you to show this combination of resources. So you may now notice that's like it's like why it's bound layer. It's really like configured to be bound to this surface, and you can actually like switch the order to give the bound layers priority you need. So this can be also done on the client. And how the result looks like. So you have this whole globe with blue marble imagery and with this really small square of high resolution imagery. A quick note that the fusion of the bound layers is physically done on the client. We just basically, the terrain we stream is preprocessed in a way that it's very easily to texture it with those textures. So that's it. Now we add some 3D models. 3D models is again a surface. That also means it will be fused with the terrain because it's the kind of same type. To actually fuse the city, we need first to convert it to VTS format. We support various kind of like widespread formats like SLPK or LOT3, and our open format, which is produced by our photogrammetric system, the VEF. And when we convert it, we fuse it with the terrain. And this is done by this simple command. When we call the VTS tool, add to storage what this tile set, the Einstein village, and add it on the top, so it will be seen over the terrain. And when this is done, it takes a while just to generate some other data that will client use to display the both data sets seamlessly. We again modify the map configuration. We have to include this data set, or more precisely, we have two data sets. I've shown the command for only one, but we have two. It's the Einstein village in the Einstein center, so we pick them from storage. We want to display them, and we add them as surfaces to the view, so they will be seen. So how it looks like, when we zoom in, the 3D will show up, and you see, yeah, this is like the whole village, and this like brighter or yeah, a bit whiter model is the city center. So here you have to see how it's actually like fused together. There is our yard from the example, so we can turn the model on and off and see the difference. There's like really new building, and there is also another yard nearby that also changed. So yeah, you can like really turn it on and off simply on the client, while it's really very heavily pre-processed on the server. So the job for the client is really simple. And the last thing we do is we add some vectors. Vectors in VTS terminology are called free layer because they can be displayed basically independently or on anything else. In this case, they can be displayed like together with the surface. It's again streamed dynamically from MapProxy. Vectors can be streamed from OGR features, like in one monolithic block, or from like proxied from MV Mapbox vector tiles, or from static database of the vector tiles, the MB tiles file. And what MapProxy needs to do, because the vector data are usually only 2D, you actually need to render them independently. You actually need to enrich them with the height, and this is also done because this is again task that is doable on the client, but it's very resource consuming. So we do it on the server. We pre-process it in the way that we just mention the DEM we want to use for height. We mention it in MapProxy resource definition, and MapProxy does the rest for us. Again, we modify our map configuration. Here we added the free layers field with the cadastral data, again streamed from the MapProxy and the path to the definition or URL of the definition of the resource. And again, we add it to the view so it will be shown when we display it. And the result looks like this. So now there are no vectors, but I can turn them on, and you can see that you will see that they are actually following like the real ground. They are not draped over the buildings like in a bumpy fashion. They follow the DEM that is specified in the definition. So you'll see it's real like snaps to the ground. Of course, you can modify the styles if you want, and so on. So that's it. So if I should conclude it, in VTS, how the fusion is done, or server-side fusion to be more specific, the terrain and 3D are fused on the server. That's the server-side fusion. But the client can still, but they are fused in a fashion that the client can still handle them as independent data, as we saw in the examples. Vectors or free layers are usually enriched with height in VTS MapProxy and displayed independently on other layers, and orthophotos as bound layers are draped over surfaces on the client, but the surfaces come already pre-processed, so the draping is really simple for the client. So in VTS, you basically can go all the way from no fusion to fuse them all approaches as you need. Like if you need fast static streaming of some static map, you can really optimize it with some more advanced techniques to nearly fuse them all approach. Or you can really render it just everything on one heap using 3 layers and have the no fusion approach. So that's the big advantage in VTS, that you can really go all the way from one approach to another. So I think that's all. Maybe we have a short time for the live demo.
Yes, thank you very much, Ladislav. Nice presentation. Do you want to show a video?
Okay.
Yes.
Yeah, just
4 minutes or
okay, okay,
3
it
or
will
4
just
minutes.
just,
and then if
simply,
there's any
so
question.
We have this demo basically. That's what is the data that we have seen. I can again turn on the vectors. Here I turn on the vectors. I can turn off this like small model. So yeah, here our favorite yards. So you can really see the difference. You can and it's like it's still global. It's not something that I just made up. Okay, so that's all from me.
Okay, nice presentation. Thank you. Do you have any question about this presentation? There is any question?
Okay.
Yes. Okay.
The volume data. Well, currently we don't work like with volume data because it's like a really like large amount. Yeah, the question was if we can work with the volume data. Yeah, sorry, that's my fault. Yeah, so currently we don't do it, but again, it's the whole solution is open source. So if you are interested, you may find some ways to put them in, either directly on the client or on the server. But currently, like there is no like walked path for that to add them there. So yeah.
Thank you. We have enough time to for one more question. Do you have any more questions? Okay, so thank you very much. We are going to finish this presentation here. Thank you, Ladislav. Thank you very much. We're going to wait 2 minutes for the next presentation. If anybody wants to come from the other room.